Now we're all set. Okay, cool. Opportunities and pitfalls, hashes. I spent the past 2 weeks in a pitfall. So I'm going to help you avoid that. And all for one little mistake. So I'll talk about what a hash is, what the hash function in particular, the built-in hash function is the one I'm talking about. There's also a hash lib that Dave and I talked about earlier, and I'll mention a little bit of that too. What is it for? What could go wrong? And I don't think I'll have time for fake news. But so hash, if you hash a string, this is what I was using it for. So I'm using it for hashing the 15 million Wikipedia titles that exist there. So I can store them in a list of integers. They turn out to be long integers, as you see here, 64-bit signed ints. And I'll show the C code in a bit to confirm that size. The idea is that you want to create a fixed size string. So even the Zen of Python, if you hashed it, would come out to a 64-bit integer that you could store as 64-bit integer. And so this is one of the nice features of that function. There's a lot of computer science-y reasons why you want it, but first I'll just explain a little bit about what I discovered looking into the source code. This is C code, so I won't spend much time here, and I've just translated a bit of it to the part that I started to see as interesting was this part here where it looks like to me it's grabbing the string value of many objects. If it doesn't happen to already be a string, it's looking for some sort of sequence of bytes, basically the bytes in RAM that it can use to represent that object. And most objects have a stir function. I'll talk about what that really is, but it turns out that's not actually what it is. But and this is for Python 2.7, but this sent me in an investigation into stir to figure out what was going on. But then once it does have a string, what it does is it does a lot of shifting of that, and it goes through each and every byte and does this multiplication by, it looks like 1,000,003, and then I'm not sure what this does. I think it shifts in C, but anyway, that's about as far as I went in terms of trying to investigate why this thing was going wrong for me. Hashing a string is what I was using it for, so I looked in a little more detail to see what was going on. So I checked to see that if the hash of the string of an object was the same as the hash of the object itself. No, that was not the case. Came out with a different string. But then I looked at the string representation of the object itself, digging a little deeper, and noticed that there's of course this ID or address location. I think at means that this is an address location. David, you can correct me if I'm off base here. And then and then I looked at the representation. It also contains that same thing. And so that gave me a clue that maybe it has something to do with this address or memory location or ID number. So I looked at the ID of an object and looked at its hash. Nope, not the same. But then I looked at the hash of the object in hex form. Sure enough, 142 at the end, and then hex of the ID, 142 at the end. They've just added an extra byte, that's all. So it's just been shifted by 1 byte, filled with zeros, at least in the address space. So it's not, the hash isn't exactly the address, but it seems to be very related to it. Pretty soon I'll stop boring you with all the math and soon get into what it's used for. Let's see. So this is how I also talk a little bit about the modulo operator, just because I wanted to create a shorter hash than 64 bits. I wanted to get it down to like 16 or 32, just so I could save on RAM for those 15 millions on tiny little servers where I want to have all these hashes in RAM. So you can use that to turn any hash. You can use this modulo operator, the %, to turn any hash into a smaller one. And that's what I'm going to use in the example for why even care about hashes? But you have to be careful about that because you'll end up with some collisions if you're not careful. And because the tighter you squeeze a bunch of different objects into one sequence of possible IDs for them, the more likely you are to have the same ID for some of those things. I'll show the documentation, which says that explicitly about what it is. This is the Wikipedia page. You can go there if you want to learn more about these hash tables that hash functions are used for. This I talk a little bit more about hashing other kinds of objects like date times. So it works on integers, but this is something that surprised me. I hashed an integer and it came out with the exact same integer. And I'll give you a special integer where that's not the case. Can anybody guess which integer does not hash to itself? And why would Python or C have something that's kind of related to an address? Why would they have a particular value of an integer not hashed to itself? They want to reserve that value for something special. Does anybody know?
0.
Not 0. That's what I would have guessed, but it's not 0. I'll do it real quick in Python so we can all get the surprise of it. So
can we ask a query this question?
I don't think it's on Wikipedia, though the Wikipedia article does mention Python's hash function because it is unique in the world of hash functions, and that uniqueness is what killed me. So if I'd read the Wikipedia article, I'd have been okay. But let's do hash 0, make sure, yep, sure enough, still 0. Hash 1 maybe? Nope. What about hash infinity? I don't actually know how to do that, but let's try it this way. Maybe that will do it. Nope. That looks a lot like pi, 3.14159. Holy cow. There's some weird stuff going on in Python. What about nan? Ooh, that comes out to 0. But the one I'm thinking of that surprised me, and you can look at the actual C code. This is why I even checked it. If you look closely at the C code online, there's a nice little if check, and they change it to -2. This is in Python 2.7. Let's see if it still happens in Python 3. And sure enough, it is. They're using that to indicate an empty location in memory, so you don't, or a null, like a non address essentially, a non-offset. So -1 is a special value in C, so they avoid it in the hashing. And also that place, that location in memory is often reserved for holding the length of an array, for instance. So if you use that in a hash table, you might get into trouble. But anyway, I like to use hash tables that I'm familiar with. You make them positive integers anyway, so you would use that mod function to wrap them around. So let's do that for these strings like Barack Obama and put them in hashes. So I want to first make sure that our hash table, so we're going to create a hash table of only 8 elements. So obviously this wouldn't work for the 15 million titles that I'm looking for and on Wikipedia, but it would work for if you only had a few strings. And so if you hash Barack Obama, no worries, it's consistently spelled, so they're going to all hash to the same value no matter how many times you do it. But then when you go to, if you misspell Barack Obama and leave out just one little letter, it'll move to a different location. And you want that. You want it to go to a different location in memory. There's another kind of hash you can use if you want them to be close to each other. One called a locality sensitive hash, or LSH. You can research that if you need those. So let's look a little bit more at the docs. This RTFM, like I didn't do. And 2 objects that compare equal must also have the same hash value. So that's what we just did with the Barack Obama hash. We confirmed that they always have the same hash value if they compare equal. I didn't check any other more complicated objects, but you get the picture. But the reverse is not necessarily true. This doesn't help me because it's actually not completely true. 2 objects that compare equal don't always have the same hash value. They're making an assumption in this documentation that I made as well, that they used to make in Python 2.7 that they no longer make. And it has to do with this whole work around for the GIL. So they have started to make Python more thread safe and more, I don't know all the reasons why down at the deep level, but for some reason this, I'm sort of giving away the answer to why this is, but I'll give another example of a collision that can happen. So sort of surprisingly, if you misspell Barack Obama and you try to hash Michelle Obama in that same address book that you've got for those hashes, you'll end up with a collision. They'll both end up at the value of 3 for this 8-bit hash that I'm doing over here. And then I'll finally, I think I'm at the end. So now we can have fun and actually discover this problem that I was having. So the problem I was having is I would hash all these Wikipedia titles. I'd look for membership in them. It would work great. I could find the Barack Obama page in this list during, as I was testing it out on my machine. Then I would upload it to DigitalOcean. I would have it be downloaded, have all my tests run on the machine, and then the hash value would not compare equal, and it would not be in that list of hashes. Now, does anybody have any ideas about what's going wrong here? So I'm gonna hash Barack Obama, and then we're gonna confirm that it's the same value that it's actually not gonna be the same value that I showed there, even if I %8. Let's just see if I %8 and see if you see what I'm seeing now. So it's now at 4. Before it was at like 7. So that means that this hash value has changed between when I put that together, that slide, and now. But if I do it now, over and over again, same value, no worries. What's going on? Anybody have any ideas? Now, do you have an idea?
Different version of Python?
Could it be
different session.
because you're creating a new object and so it has a different?
All you have to do is start a new session.
Oh, that's right.
I created a new object there. Barack Obama, when I create that string literal, that's a new object, new address space, a new address ID. Everything's changed about it. You can do this with other objects as well, and you'll find the same thing. It's crazy. It totally caught me off guard. And it cost me 2 weeks of trying to figure out, okay, I must have a typo somewhere in my code somewhere. I must be doing something wrong. But it was actually Python itself that was fooling me. So that I would love it if that if this documentation said 2 objects that compare equal must also have the same hash value within a session. If it just said that, that might have caught me and helped me realize this. But it's not true across sessions. Let's see what else. Was any other fun things I discovered about hashes? I guess that's about it. So we moved to a library that is more consistent. So let's just do that. Oh, and also the other thing is Python 2.7. That would have worked just fine. Import. I said I don't even have to import anything, do I? Hash Barack print. Oh, I'm gonna have a quote problem here. So they do great. Python 2.7, no worries, always the same. Python 3, no such luck. So be aware of the big changes they made to the efficiency of Python 3 to distribute these hashes more uniformly. What they did, oh, that's what I forgot to mention, is there is this Python hash seed. So you can create a Python hash seed. I think it's supposed to be an integer, but then that will make them consistent. And I just need to make it an integer. And now they're consistent across sessions. So if you want them consistent, you can revert to the old Python 2.7 behavior if you just set a fixed hash seed. What they did is they added salt to the hashes, and they changed the salt integer in Python 3, and they recreate it every session, unless you specify it and tell it you want it to be the same. I haven't just, I'll do one last experiment that I haven't yet experimented with. I think import os.environ. Let's see if I can do Python hash seed. Great. Now let's see if we can, so we'll do that hashing again. Oh, we got a 0 this time. Now let's see if we change the OS environment hash seed to something like 43. Oh, it needs to be a string that represents an integer. Interesting. It does not change that hash seed. So once the session is launched, once the hash function has been created, that hash function is fixed and compiled in RAM, and you can't change the hash seed to make it change the behavior so that you get a new kind of salt. I don't know at least how to do it. You can't do it by changing the environment variable. I just learned that just now. So I will not try to do that in my Python sessions because it's unlikely to solve that problem. So I can't like just put at the top of my settings file in Django, set that hash seed in the environment and hope that it's going to now make my hashes consistent. I'm going to have to use the MD5. So I went to MD5 in the hash lib because that is consistent, doesn't include any salt that you don't control. You get to decide what the salt is when you create an MD5 hasher or a SHA-256 or a SHA-128. That's me. Any questions?
That's
Thank
actually
you.
very cool. I did post in the chat that having a non-randomized hash was considered a vulnerability in Python. And I remember hearing Brendan Rhodes give a talk on dictionaries, and dictionaries uses hashes to decide where to put items in buckets. And there was actually a way to DDoS to the point where you would slow the Python interpreter to a crawl by submitting custom crafted objects to do that. So that's why they changed that.
So that somebody else can't predict what your hash function is going to hash to.
Correct.
But they could if you didn't have the salt. I got it. Sweet.
Yeah, the rationale's in the chat if you want to take a look.
Because then you could force it, you could send a bunch of objects that look different and should hash differently, but you know that they hash to the same value, and then you could hose Python. Very cool.
Any other questions? That was super cool. I learned a lot.
Awesome.